So what we get, I know you can't read that. It's very difficult to read. So let me write it for you. It's 2s squared, 4s squared divided by 4s squared plus 1 plus 2s. Okay? So this is the name of the game. Use the parallel and series rule here. We use voltage divider, parallel rules, series rules, and then we simplify. And it really makes your life a whole lot simpler to use S for J2 pi F. So this is what you get, and now I can write it in terms of F, which is what we need to do in order to solve for our sinusoidal source. We need this H of F, and here it is in all of its glory. So S squared is going to be 4 pi minus 4 pi F squared times the 4 gives us a 16, etc. So this is what it is. So at this point, what I would like to do is find the frequency of the source. So the frequency, this has to be written as 2 pi ft. So 2 pi f has to be a half for this example, which means the frequency is 1 over 4 pi. Kind of a strange frequency, but it really simplifies the calculation, which for this example. I now want to find the value of the transfer function at that frequency. And like I said, this is really makes this assumption of that frequency value really makes the calculations very simple, because the numerator just turns out to be -1. We get that same term here. This becomes j, and the 1 is 1. So we get -1 over j, and the reciprocal of j is -j. So we get j for an answer. So our transfer function at the frequency of the source, that's all we need to know, is what the transfer function is at the frequency of the source, is j, a pure phase shift. So, now we get to figure out what the output is. So, I'm going to think about our sinusoid as being the imaginary part, since it's a sine wave, probably makes it easier, as 10 e to the jt over 2. Well, we know that the output is going to be the imaginary part of 10j e to the jt over 2, where j is that transfer function evaluated at the frequency of the source. And j, again, that's in Cartesian form, convert to polar form, and that's our answer. And I know from the trig identities that that's just cosine. So we stick in 10, and it turns out it's a very special frequency, because what this circuit does at that frequency is convert the sine to a cosine, and it has the same amplitude. That's really pretty surprising, but again, I've chosen a frequency that makes the calculations easy, and that's basically why that happened. In general, as we know, it's going to produce a sine wave at the same frequency with a different phase and a different amplitude. You choose a different frequency, this amplitude will definitely be different than 10. Okay, now I've taught this course for many years, and I've learned what students do that isn't correct. So I want to talk a little bit about what not to do, how to use impedances. So here's the name of the game. We start with a circuit. We know the input. We write it as the imaginary part of something, and we find the transfer function, and we evaluate it at the frequency of the source. And we now know, since I used imaginary part here, that that we use imaginary part here, and that's the correct approach. Okay. Transfer function evaluated at the frequency of the source, we get that from that formula, times the complex amplitude representing the source along with its complex exponential frequency. We take the imaginary part. Well, I have seen students do the following. They just say, well, is the sinusoidal source. He told me it's just the transfer function times that. Well, that's clearly wrong. At least in this example, we know that the transfer function of that frequency is j. So why in the world would you put in a real valued input and come out with something that's complex valued? This is wrong. You have to think of the source as a complex exponential, and then things go through. So this is not correct. Another thing that isn't very good is to mix the two things together. So you just stick in the source, multiply by the transfer function at the right frequency, and take the imaginary part. Well, that's not what you have to do. There's this intermediate step. Remember, pretending the source is a complex exponential. That's the right formula. This is wrong. Okay, so I hope this helps. We now know a very general result. The output for any sinusoidal input of a circuit is going to be a sinusoid at the same frequency, and the way we find it is by converting to complex exponential form and then multiplying by the transfer function and taking the real or imaginary part depending on how we chose to do. We'll learn more about how to use impedances to figure out what these kind of transfer functions do and to get a much more general, broader picture of circuits.